Welcome back to Science Fantastic with Professor Michio Kaku. On Science Fantastic, we profile the amazing, jaw-dropping scientific discoveries which are revolutionizing the world and touching our lives. And in this hour, once again, we're going to throw the lines open because this hour is your hour. Okay, let's move on now to the first listener phone call.
Earl Smith, listening to KEYS in Corpus Christi, Texas. I have a question. I understand that on a number line between, say, number 1 and number 2, there are an infinite number of points. But how is it that I can arrange my finger to be 90 degrees to the number line, and I can run my finger across that line and pass over each one of those points? Thank you.
Well, you ask a variation of the Zeno paradox, which is literally 2,000 years old. Zeno, the great Greek philosopher, had a proof, and the proof was that motion was impossible. That's right, nothing can move. And he proved it exactly the way you mentioned. If I take a river and I mark 2 points on it, the beginning on one side of the river to the end of the river, and then I ask a simple question, how long does it take to go between 2 points? You realize that there are an infinite number of points between point A and point B, and it takes an infinite amount of time to go through an infinite number of points. Therefore, said Zeno, nothing can move. Motion itself, he said, was impossible because it takes an infinite amount of time to pass through an infinite number of points. Ergo, motion was impossible. Well, on one hand, people thought he was nuts. I mean, what? Of course things can move. But if you think about it, how many points are there between points A and B? And then you begin to realize, hey, this is really a deep question. And it was finally solved by people like Isaac Newton and the mathematicians of the 17 and 1800s when they invented calculus. They showed that it takes a finite amount of time to move through an infinite number of points if you very carefully divide up the interval and take the limits correctly. And so this is the beginning of calculus, which on one hand seems impossible because you are talking about dividing up a point into an infinite number of intervals, and motion, which obviously exists. I mean, things obviously move. Any idiot knows that. But if you think about it, what is the smallest distance? Well, today we have a more modern view of that question, and that is, what is the smallest distance between 2 points? We once thought it was the atom, that the atom was the smallest object, and therefore the atom was the smallest distance that you could make between 2 points. But now we split the atom. We have now protons and neutrons, which are even smaller than an atom. And now we can even bust up the protons into quarks. And so we're back to Zeno's paradox again after 2,000 years. What is, therefore, the smallest distance? Well, we're not sure. But many physicists believe that the smallest distance is the size of a string. The string is extremely small, 10 to the minus 33 centimeters, is the smallest distance that has ever entered the annals of physics. And we think that that is the smallest distance of all. And that, therefore, Zeno, in some sense, was onto something. He thought this went on forever. But we physicists think, no, it stops. We're not sure, but we think it stops at the size of a string. And if you want to know more about string theory, get a copy of one of my earlier books, Hyperspace, which talks about vibrating strings in 10 and 11-dimensional hyperspace. We think that is a theory that eluded Einstein, because Einstein wanted a theory that would allow him to, quote, read the mind of God. So find out more about this by getting a copy of my earlier book, Hyperspace. Okay, let's move on now to the next listener phone call.
This is Janice Miller, and I'm calling from Corpus Christi, Texas. and the station that I'm listening to is KEYS Radio. And I've listened to you many times before when you were at 4 o'clock in the afternoon. And I just want to tell you, even if I'm not able to get on to speak to you, I really have enjoyed your program. You're a real thought provoker. My question is, with all this robotic stuff, where does faith and religion and feelings come in? Thank you. This is Denise Miller.
Well, you asked one of the big questions, and that is, what is the relationship between humans and robots as we go into the future? Are robots going to be unfeeling? Are we going to become more robotic? What is the relationship when robots gradually approach human intelligence? Well, first of all, let me give you a time frame. Robots today have the intelligence and emotional ability of a cockroach, so don't expect robots to replace us anytime soon. However, let's take a short commercial break, and after the break, we'll talk about robots that can feel, robots that have emotions, and what does it mean when one day robots can be emotional? Welcome back to Science Fantastic with Professor Michio Kaku. On Science Fantastic, we profile some of the most amazing developments in science. And before the break, we had a question from a listener asking about, well, what happens when robots gradually become like us? And then the question is, what about emotions and feelings? And how close can robots come close to us? Well, first of all, there is such a thing as a science of emotions. At MIT, for example, at the Artificial Intelligence Laboratory, they're trying to create emotional robots. Now, you may say to yourself, why? Why would anyone want to create a robot that can cry or laugh? Well, first of all, some of these robots already have a practical application, and that is they're used in nursing homes where people get lonely and need a companion, and they want to talk to something. Of course, you can't have a caretaker there 24 hours a day. However, emotional robots are one pioneering area that MIT scientists are looking into. First of all, it's rather easy to simply understand the emotions of the face. Face recognition technology already has given us the ability to identify anger and puzzlement and things like that in the human face. That's not the problem. Also, we can mimic the muscles of the human face to mimic fear and mimic joy and things like that. That's not the problem either. The problem is to figure out when things are appropriate. Because if you give the wrong emotion for a certain situation, people get insulted. They get angry. If, for example, you're grieving because a relative died, and here's this wiseacre robot laughing and joking, you get insulted. And so it's much more complicated to figure out when certain emotions are to be required and when certain emotions are not to be used. But again, the first application is in places where we have loneliness. And we also see them in Japan. In Japan, where we have an aging population, and also at MIT, where we have experiments done on nursing homes, we find that these emotional robots are actually quite good, that they do give a sense of companionship to people who are normally lonely and cannot afford to have 24-hour care. That, of course, is not the real thing, but it's better than nothing. And as time goes by, we'll have robots that are more and more accurate in terms of their understanding the emotional state of another person. Now, if you watch Star Trek, there is Data, the robot that wants to become human. And we find that things are done inappropriately. Data laughs at the wrong points, misunderstands simple human behaviors, and it's going to take time. But it's not out of the question. The difficult thing is to figure out when certain emotions are appropriate and when certain emotions are not appropriate. And then the next question is, can the robots really feel this thing, or is it simply mimicking, like a tape recorder, an emotion? In other words, if a robot seems to cry, is the robot really crying because it feels bad, or is it simply pushing a button that says, time to cry? Well, I think the two are quite different today because our technology is quite primitive. But as time goes by, in the future, the two will become indistinguishable. That is, robots which can push the button which says, time to cry, and actually, quote, feeling crying, feeling sadness, will become closer and closer with time, so that for all intents and purposes, we will be able to interact with robots that feel sad. Now, I should also point out that there's something called the uncanny valley. Now, let's say that you get a robot that is emotional, but it's not quite there, doesn't quite look human, but tries to be human, and makes emotions that are slightly inappropriate. What do? You get the creeps. You say, this is really creepy. For example, think of Halloween. During Halloween, what do you have? Inappropriate emotions. You see ghouls and monsters smiling at you. And it freaks us out. We feel really creepy seeing somebody that is obviously a monster grinning and smiling at us. So inappropriate emotions make our skin crawl. And this is called the uncanny valley. If a robot is quite unhuman looking, we can look at it, laugh at it, and analyze it. But as it becomes more and more human-like, and still makes slight mistakes and is not quite looking human, we get a creepy feeling, and that's called the uncanny valley. And then, of course, when the robot has perfect emotions and perfect feeling, then we accept it as a sentient being. But before then, we get the creeps. And, of course, at Halloween, many people who make Halloween masks know this, inappropriate emotions. And that's going to be a problem for robots for quite a while to get the emotions right. For example, one scientist pointed out to me that if you have a father with a towel slapping the butt of a son, on one hand, the son can say, oh, my father is being playful, and the son will start to laugh when the father whips a towel at the son's butt. But if it hurts, and the father starts to grin in a bad way, then the son starts to cry because he knows that it was meant as punishment. So the slightest difference in a person's facial expression can signal the difference between happiness and sadness. And at the present time, robots are far from being able to master these simple emotions. Okay, let's move on to the next listener phone call.
Paul Kruger, Interlochen, Florida. I'm just responding to a tweet. This is the question. In the search for dark matter and dark energy, is there a possible link between these and primordial antimatter? What became of the energy released when said antimatter was annihilated by matter at the time of the Big Bang? And could that be related to dark stuff?
Well, you ask a question for which there's no simple answer, but first of all, let's define the terms. Dark matter, we know exists, but it's invisible. And we have maps of dark matter, but no one's ever seen dark matter on the planet Earth. Therefore, it's one of the most mysterious of all substances, but ironically enough, it makes up most of the universe. Most of the matter, by a factor of 10, most of the matter in the universe is actually not ordinary matter at all. Is dark matter. Then there's dark energy, which is the energy of the vacuum. It is also invisible, and it is responsible for pushing the galaxies apart, and that's called the Big Bang. So you got that? Dark matter surrounds the galaxy, holds the galaxy together, is invisible, but is ordinary matter. Then we have dark energy, which is energy that is pushing the galaxies apart, and that is causing the expansion of the universe. Then, if that's not complicated enough, we have antimatter. Now, antimatter already exists. It was postulated around 1928 by physicist Paul Dirac. And he realized that Einstein's equation, E equals mc squared, was not quite right. When you take the equation E equals mc squared, which even children know, you have to take a square root. And therefore, it's actually E equals plus or minus mc squared. I repeat, Einstein's famous equation is actually slightly wrong. Einstein, of course, knew this. The correct equation is E equals plus or minus mc squared, but the minus was once thought to be rather useless. I mean, who needs negative matter, right? Well, this is where antimatter comes in, because then Dirac stated that, well, you just can't throw away the minus sign. It has a role to play, and that is antimatter. Now, antimatter is visible. We don't know what it looks like, but if you had enough of it, it should look like ordinary matter. It has all the electrical properties of ordinary matter. And so we think if you have anti-atoms, you can eventually create anti-molecules, and eventually anti-objects and anti-people. That's right. We think we can create people made out of antimatter. And of course, we haven't done that. We've only made tiny snippets of antimatter in the laboratory. In fact, when I was in high school, I played with antimatter for my science fair project. So then the question is there a relationship between all three? First of all, antimatter is not dark matter. We can rule that out right now, because dark matter does not have charge. Antimatter does. And so we can rule that out immediately. But what about dark matter and dark energy? The short answer is we don't know. However, let's take a short commercial break, and after the break, I'll give you the leading theory about what dark matter is. Welcome back to Science Fantastic with Professor Michio Kaku. Once again, the lines are open. For the break, we had a quick question about three things: dark matter, dark energy, and antimatter. What's the relationship between all three? First of all, antimatter exists. We create beams of antimatter at the Large Hadron Collider outside Geneva, Switzerland. So antimatter is not the mystery that it used to be decades ago. In fact, on Star Trek, it is absolutely true that maybe one day we'll have antimatter engines. Not at the present time. Antimatter is extremely expensive to make. It would cost trillions of dollars to make even a few grams of antimatter. So antimatter is not so mysterious. But dark energy is mysterious. We simply don't know what dark matter and dark energy are. Dark matter holds the galaxy together, so we know how important it is. Without dark matter, our galaxy would have flung apart billions of years ago. The leading theory of dark matter, which is not proven, the leading theory is that it's a higher octave of the string, that we are the lowest vibration of tiny vibrating strings. The universe is a symphony of strings, and we just happen to be the lowest octave. However, everybody knows there are other octaves out there, higher notes. And these higher notes have names. One of them is the photino. And the photino is, in fact, the leading candidate for dark matter. So we think that dark matter is ordinary matter vibrating at a much different frequency, and the frequency given by string theory. And if you want to know more about this, get a copy of my book, Parallel Worlds, where I talk about dark matter and string theory. Okay, let's move on to the next listener phone call.
Hello, Dr. Kaku. My name is Albert. I'm in San Jose, California. First of all, as always, I think it's a great honor to be able to ask you a question. First of all, about parallel universes and time travel, I'm a little bit somewhat confused. I want to ask you something about this. Suppose you want to go back in time, that there's a method. Now, the steps involved in the method, how would you choose which parallel universe to go back into time to avoid the paradox? In other words, if you go back in one parallel universe that does not, maybe nature has somehow safeguarded, if I'm not, correct me if I'm not right, nature won't allow us to go back in time in this same universe, only in parallel universes. to avoid the paradox. So I just wanted to clear that up a little bit. So yeah, if you go back in time, okay, and let's say you always had that little example of you met your mother and you fell in love with her and so forth and so on. I found that a little amusing. But it's true, though. Then there would not be any type of paradox, would it? Thank you.
The simplest time travel, which gives you a paradox, is you go backwards in time and meet yourself as a young kid, and then you kill him. What happens? You just committed suicide in the past, so how could you be born? How could you be alive to go backwards in time when you just killed yourself in the past? Or what happens if you go backwards in time and your mother falls in love with you before you're born? How can you be born if your father and mother never got together because you interfered? Well, the brain goes crazy thinking about these things, but let me summarize the state of affairs. First of all, Einstein thought that time is not a straight arrow like Newton thought, but more like a river which can bend and meander. And the new wrinkle that even Einstein realized is that the river of time can have forks in the river of time and whirlpools. If you have a whirlpool in the river of time, then time travel is possible, and all the paradoxes of time travel have to be taken very seriously. And then in 1949, Kurt Gödel, the famous mathematician, one of the greatest mathematicians of the millennia, came up with a solution of Einstein's equation which did allow for time travel. If the universe rotated and you were to go around the rotating universe, you'd go backwards in time. Einstein was disturbed. He was really disturbed because here was a solution which seemed to defy common sense, staring at him in the face. In Einstein's memoirs, he said that we can dismiss this for physical reasons, i.e., the universe does not rotate. The universe expands, as in the Big Bang, but it means that if the universe did rotate, then time travel would be commonplace. Well, Einstein thought that was an anomaly, but since then, we physicists have discovered scores of time travel solutions, which makes things embarrassing. In fact, we even give them a name, CTC, closed time-like curves. So if you want to know how a scientist views time travel, don't Google time travel. You'll get all the science fiction. Instead, Google CTC, or closed time-like curves, and you're going to find out how real physicists deal with time travel. Now, how do we deal with the paradoxes? There are several ways of dealing with the paradoxes. The first way is something I don't believe in, and that's been proposed by Professor Novikov of Russia. And he says when you go back in the past, things are self-consistent, so it was meant to be that way. You, in some sense, fulfill the past. It was meant to be that way, and there are no paradoxes. Well, personally, I find that really hard to believe, that if you go backwards in time and really mess things up, then it was meant to be that way, and so there are no paradoxes. I find it a little bit hard to believe that. I believe in the quantum theory, which simply says that you enter a parallel universe. In quantum mechanics, which is the leading theory of all matter, like atomic physics that we teach in graduate school, time can fork into two rivers. Each time a decision is made, the river of time forks into two rivers. These are called quantum events. And it simply means that if you go backwards in time, you enter a different time stream. So that when you save Abraham Lincoln from being assassinated at the Ford Theater, you're saving somebody else's Abraham Lincoln, not your own Abraham Lincoln. So there are no paradoxes. This means, of course, that there could be other parallel universes where things are messed up and things really are goofy, but that's a whole other question. So what does this have going for it? What it has going for it is that quantum mechanics, no matter how goofy it sounds, is really true. It really is the way things are. That our brain, which is classical and Newtonian, our brain which believes that everything happens in definite states, that the past is the past and the future is the future, well, that's wrong. There are apparently other parallel universes. And then the last question that everyone asks is, can you go between universes? That is, if you go backwards in time, and let's say you wind up in a universe that you don't like, can you go backwards again and enter a different universe? Or let's say in one universe, a loved one is alive. In another parallel universe, a loved one is dead. Then the question is it possible to go between universes to bring back the dead? Well, it turns out that in principle, quantum mechanics does allow you to go between universes, but it is astronomically difficult. Don't expect anyone to do that anytime soon. In other words, it takes an energy of a black hole, fantastic energy, to do this. And it's not going to happen anytime soon. But let's take a short commercial break, and after the break, we'll get more into traveling between parallel universes. Welcome back to Science Fantastic with Professor Michio Kaku. Before the break, we had a question about time travel. What do physicists think about going backwards in time to perhaps a parallel universe? Would that allow you to solve all the time travel paradoxes, like what happens if you kill your parents before you're born? And the answer is yes. If you wind up on a different timeline, then you kill your parents before you're born, then it turns out that the people that you just killed look like your parents, have the same genes as your parents, but are actually copies of your parents in a parallel universe. That's how we get around all the time travel paradoxes. So take any movie that you've seen about time travel, and draw a timeline, and you can see how the timeline splits and breaks apart, but you can graph exactly what happens each time you enter the time machine. So there are no paradoxes. And then the last question is, can you move between parallel universes? In principle, the answer is yes, but to open up a parallel universe requires enormous amounts of energy comparable to a black hole. So don't think that any inventor is going to create a black hole and a time machine in their basement. It's not going to happen anytime soon. Now, some people think maybe there's a loophole there, because it turns out if you look at Einstein's equations very carefully, it depends on the speed of light. Therefore, if you could alter the speed of light, then the amount of energy necessary to build a time machine can be made smaller. In fact, there are some people who say, aha, that's the loophole in Einstein's equations which allow for time travel. Change the speed of light, which you can do in the laboratory. Well, not so fast. It turns out that in the laboratory, you can slow down time, but it's an illusion. In fact, I once took a film crew to Harvard University where we filmed this effect. We actually filmed the effect of light slowing down. Now, how does that work? Light in a vacuum always travels at the speed of light. So between two atoms, light is traveling at the speed of light. But when it hits an atom, it gets absorbed, and then a fraction of a second later, it's shot out again with a time delay. So the time delay gives you the illusion that light has slowed down. It hasn't slowed down at all. Between atoms, the speed of light is the speed of light. But because it hits an atom and is absorbed and then re-radiates a split second later, there's a delay time. For example, think of the early Pony Express. Remember way back in the 1800s, before telegraph wires came in? People would get on horses and ride horses between point A and point B. Once they went to point B, they would rest, get on another horse, and then shoot again to point C. Well, of course, between outposts, you were traveling at the speed of a horse. But the average velocity was much less, giving you the illusion that the speed of the horse was less than it really is. So that's how the so-called loophole in Einstein's equations is not a loophole at all. In other words, to sum up, sorry about that, time travel still is extremely hard to perform, requiring energies comparable to a black hole. And we can barely control the energy of a furnace, let alone the power of a star or even that of a black hole. Sorry about that. Okay, let's move on to the next listener phone call.
My name is Chris Nelson. I'm calling from Toronto, Ontario. I have a question. During the last post-extinction of mankind 70,000 years ago, is it possible that we were evolved enough and smart enough at that time to build the pyramids, to have built Atlantis, to actually had the vehicles that had flight, that we actually carved all the lines in Peru? That's my question. I'll wait for your answer. Thank you.
Okay, well, you ask a very interesting question. Let's break it down into its components. Yes, first of all, 70,000 years ago, roughly speaking, something happened that was catastrophic that killed off most humans. By looking at the DNA, you can recreate a genetic map of the human race showing that there is a pyramid, and at the tip of the pyramid is when early humans regenerated the entire human race. Something wiped out almost the entire human race, leaving only, a few hundred, maybe 1,000 people to repopulate the entire earth. Some catastrophe happened, and if you go to the geological history books, there was something catastrophic 70,000 or so years ago, and that was the eruption of the Toba volcano in Indonesia, which blanketed Africa with soot, changed the weather, destroyed much of the life and vegetation in Africa. And we think that's the reason why only a handful of us, a few hundred of us, survived to repopulate the entire human race. Now, that was about 70,000 years ago when it was still in the Ice Age. Then, 10,000 years ago, something magical happened. Because before then, we were still savages. We operated in small tribes of maybe 100, 200 people. We were scavengers in the ice. It was a hard living. Cities did not exist because, of course, if the buffalo left, if the antelope left, and you were still there in a city, you'd starve to death. You followed the game. This was before farming. As a consequence, we lived in small pockets with no accumulated technology. The technology necessary to cut stone and to create advanced tools and clothing did not exist because we had to carry on your back everything that you owned. We were nomads. Nomads going between point A and point B, desperately trying to find food. Then the ice melted 10,000 years ago. Then we started to get cities and accumulate knowledge, which then gave us about 5,000 or so years ago, the pyramids. And so the technology of the ancients, talking about Atlantis and cities and stuff like that, that's recent on a scale of maybe 4,000 to 5,000 years, but the extinction event was 70,000 years ago. Okay, well, unfortunately, that's it for Science Fantastic. Welcome back to Science Fantastic with Professor Michio Kaku. On Science Fantastic, we profile the amazing, jaw-dropping scientific discoveries which are revolutionizing our world and touching our lives. And in this hour, once again, we're going to throw the lines open because it's open mic. That's right, open mic on Science Fantastic. Okay, well, let's move on now to the first listener phone call.
Hi, Dr. Kaku. My name is Lance. I'm calling from Green Bay, Wisconsin. I was just wondering, what would happen if two big bangs were to collide against each other? I want to eventually write a science fiction book just for fun, and as that would be something I'm curious about. So, wonder what you were thinking about two big bangs colliding each other, what happens in the middle. Thank you.
Well, you ask a question that, by golly, we physicists are also asking. The theory is called inflation, which actually fits all the data. It is the leading theory of creation. And my colleague Alan Guth of MIT, who I've actually had on radio, may eventually win the Nobel Prize in Physics for inflation. Inflation says that the universe was born in a tremendously cataclysmic event, much bigger than previously thought, but it was a quantum event. In other words, there's a certain probability that could happen again and again and again. In other words, big bangs could be happening all the time somewhere out in the universe. So if our universe is a bubble of some sort and the bubble is expanding, that's a picture given to us by Albert Einstein. They were like insects living on the skin of a gigantic bubble that's expanding. But we now believe that the bubble can bud a baby bubble, or baby bubbles can collide to give you a bigger bubble, and that could give you a mini Big Bang. In other words, the leading theory is, the theory of the multiverse, that we coexist with other universes. These other universes can collide with us, creating an even bigger Big Bang, or they can peel off and create a baby universe. This is called the multiverse theory, and it's taken the field by storm because it is a quantum theory. You see, Einstein's theory is not a quantum theory. In fact, Einstein himself had reservations about the quantum theory. So Einstein basically thought that the Big Bang happened once, and only once. End of story. But you see, in the quantum theory, there's a probability that you can exist in different states. So if the universe popped into existence one time, why not a second time or a third time? Or why can't they even collide? And so, believe it or not, we physicists are actually looking at the possibility of colliding universes. I was at a talk a few years ago given to us by another theoretical physicist, and he asked himself a simple question. Let's say our universe collided with another universe billions of years ago. How would we prove it? What kinds of data would we need to prove the existence of a pre-Big Bang or a pre-collision with another universe? Well, you see, we have, believe it or not, baby pictures of the Big Bang. If you go to nasa.gov and look under COBE or WMAP, you can actually see a picture of the microwave radiation emitted about 300,000 years after the Big Bang. By golly, it looks like an explosion. Because it is an explosion. We have photographs of the microwave radiation emitted from the Big Bang itself. Now, here's what we physicists do with this data. We look for irregularities in this picture. It looks like an explosion, and like I said, you can see it on the web. It's an explosion in the microwave range. And we look for irregularities, and by golly, we do find some of them. Now, these irregularities could be remnants of a previous collision that we had, maybe with a smaller universe. So, believe it or not, we physicists are actually looking at slight deformations in the afterglow of creation itself. And we hope to use these aberrations in order to prove that, once upon a time, we collided with another universe. So, yeah, it's science fiction, but this is now fair game for physicists who now believe that once you marry the quantum theory to Einstein's theory of the Big Bang, then all hell breaks loose. Parallel universes, a multiverse of universes, maybe even the laws of physics themselves could be different in other parallel universes. And then people ask me the question, well, if there are other parallel universes out there and we can collide with them, is Elvis Presley still alive in another parallel universe? And one day, could we meet him? Compliments of the multiverse. Well, you can't rule it out. There's a certain finite probability that, that the king is still alive in another parallel universe. But when you calculate the probability, it is so small. It's finite, but so small, I wouldn't worry over it. Welcome back to Science Fantastic with Professor Michio Kaku. The lines are open, and it's open mic in this hour. Let's go to the next listener phone call.
Hi, my name's Billy. I'm calling from Collinsville, Illinois, and I mostly listen on YouTube. I have a two-part question. Part one, string theory, from what I understand, says hyperspace is at least 10-dimensional, but you theorize it's 11. Why is it that it only needs 10, but you postulate it's 11? Part two of my question is, well, hyperspace states that our four-dimensional universe is a bubble in hyperspace. Our universe is expanding in all directions infinitely and is actually increasing in its expansion, which scientists attribute to dark energy. For someone who believes in string theory, if asked what's on the other side of our universe, the answer I would imagine would simply be hyperspace. That's what we're expanding into. But for someone who believes in another theory, that answer isn't as simple. I would say right on the other side of our universe would be our temporal dimension. If our temporal dimension could permeate through and past our three special spatial dimensions, could it be that our time dimension is dark energy? That is to say, could our time dimension, since its original expansion, be pulling our universe outward? Which would mean that maybe hyperspace doesn't have or need a temporal dimension, and that our temporal dimensions will one day reach the vastest corners of hyperspace. And finally, would that mean that things that exist only in hyperspace exist outside of time? Thank you very much.
Well, the answer to your question is yes. Next question. Now, let me try to make a stab at some of your questions, which really go to the very cutting edge of science itself. First of all, many people have seen that Oscar-winning movie, The Theory of Everything, talking about the life of the late cosmologist Stephen Hawking. The movie, The Theory of Everything, won the Oscar. But, ironically enough, you can watch the entire movie and they never tell you the name of the theory of everything. And the name of that theory is string theory. We think that's a theory that eluded Einstein for the last 30 years of his life, from 1925 to 1955. He worked on a theory which would unify all the laws of nature into a single framework. And unfortunately, he died before he could complete that process. Well, today, of course, I can read that book. I can read Einstein's book. I can see all the different trails that he went into that were eventually dead ends. One promising trail was to go into hyperspace. Einstein talked about the fourth dimension, 3 dimensions of space, 1 dimension of time, and the possibility of a 5th dimension, but he didn't go far enough. We think that in 10 dimensions, something magical happens. That in 10 dimensions, not only do you have particles like electrons, which are dots, but also you have strings emerging, and these strings can vibrate, and each vibration corresponds to a subatomic particle, and that's why we have so many subatomic particles. They're nothing but musical notes on a tiny, eensy-weensy little violin string. So think of a rubber band. A rubber band from a distance looks like a point. But close up, you see that it's a rubber band that can vibrate in different modes. Each mode is a subatomic particle. So if I could photograph an electron, magnify the photograph, I would see that it's not a dot at all. That the electron, which is in your cell phone, is actually a vibrating rubber band. But if it vibrates at different frequencies, it becomes a different particle. So physics is reduced to the harmonies of 10-dimensional strings. And chemistry is nothing but the melodies you can play on these strings. And the universe is a symphony of strings. And what is the mind of God that Albert Einstein spent 30 years of his life chasing after? The mind of God is cosmic music resonating through 10-dimensional hyperspace. Now, the listener asked a question. What about the 11th dimension? Well, you see, there are some problems. First of all, in 10 dimensions, you can summarize all of string theory into an equation 1 inch long. In fact, that's my equation. Google string field theory, and that's one of the things that I created, which allows you to summarize all of string theory into an equation about 1 inch long. So, what's the problem? There's always a problem someplace, right? It turns out that in 10 dimensions, there are not 1, but 5. 5 different self-consistent string theories. Now, we physicists tried to ignore this problem for many years, but it kind of was always gnawing at us that there are not 1, but 5 different string theories in 10 dimensions. And then the people at Princeton discovered that if you add 1 extra dimension, you go to 11 dimensions, then these 5 strings coalesce into 1 membrane. And this shook up the whole field of string theory. We now began to realize that maybe strings themselves are not fundamental, that there's a membrane living in a higher dimension, the 11th dimension, which can give us another theory called M theory. Now, it turns out that, well, it could be right. I think so. That why would God create a universe with 5 separate string theories, each of which is capable of describing our world? Why not one theory in 11 dimensions? And that's what many physicists are working on now, M theory. Now, is there a similar equation to the one that I wrote years ago, summarizing all of the theory into an equation 1 inch long? And the answer is no. If you want to become famous, then try to summarize the 5 different string theories into a single equation in 11 dimension. It turns out that some of the brightest minds of the universe, the brightest minds on Earth, have tried to do that and have failed. In fact, that's what I'm working on now, trying to unify the 5 different string theories into one membrane in 11 dimensions. And then the questioner asks yet another question about dark energy and temporal dimensions. So let me try to explain. Our universe is 4-dimensional. That is, it has 3 dimensions of time. 3 dimensions of space, and 1 dimension of time. But even Einstein believed that it was nothing but a bubble of some sort. But what is the bubble expanding into? Even children ask that question. If the universe is expanding, what is it expanding into? Well, we think it's expanding into a greater arena of hyperspace, 10, possibly 11-dimensional hyperspace. So in other words, it was Shakespeare himself who said that the universe is a stage, and we're actors and actresses making our entrances and exits on the stage of the universe. Well, that was the picture adopted by Isaac Newton. Then along comes Einstein, who says, not so fast, not so fast. That stage is warped. That stage is curved. And that gives you the illusion of a mysterious force pervading the universe, because the universe is more than just a stage, it's a warped stage. Well, now we believe that that stage of life is nothing but a ball of some sort, a bubble floating in a much bigger stage, 11-dimensional hyperspace. So now imagine a stage with soap bubbles on it. Lots of soap bubbles popping into existence, popping out of existence. That's the new theory, the theory coming from string theory of hyperspace. And dark energy is the energy pushing the galaxies apart. So when children ask the question, why is the universe expanding? We think that it's dark energy, the energy of the vacuum, the energy of an empty bubble that is pushing the galaxies apart, creating the Big Bang. That's why the universe is expanding, because of dark energy. Well, if you want to find out more about this, get a copy of my earlier book, Parallel Worlds and Hyperspace, because they go into much more details about the cutting edge of science itself, which is now trying to unravel the instant of creation. Okay, well, let's move on now to the next listener phone call.
Hi, Michio Kaku. My name is Jonathan. I am living in San Francisco, and I am a SF State student. I have a question that's been bugging me. There's been talks about this whole, if our universe is actually a simulation, and
okay, yeah, I'll answer that question after the break about a simulated universe. Once again, you are listening to Science Fantastic. Welcome back to Science Fantastic with Professor Michio Kaku. The lines are open, and it's open mic in this hour. Now, before the break, we had a question. I had to cut him off, sorry. A question about, is the universe a simulation? Is it nothing but a computer program? Is reality a fake, in other words? Sometimes late at night, you turn on the TV, and you watch these old movies on TV, And then you ask yourself a simple question. Well, these actors and actresses on the TV screen, do they know that they're nothing but images on electrons on a TV screen? That they're not real? Well, you begin to wonder, is reality itself an old movie? That is, did someone hit the play button and a CD-ROM starts to whirl, and we are like those images you see in an old movie on TV late at night. We act as if we have free will. We act as if, in the movie, as if we can make a decision. But you know the ending. You know the ending of the movie. It's just a movie. And so then the question is that reality? Is reality itself just a movie? And we're dancing on the stage of life, thinking that we have free will, thinking that we can decide the future, when actually we're nothing but celluloid on a celluloid film inside a CD that somebody hit the play button with. Is that possible? Well, computers are getting more powerful all the time, and we can begin to simulate things like airflow on a jet plane. We can begin to simulate the DNA molecule. And so people begin to think, well, I saw the movie The Matrix, and in the movie The Matrix, the robots are so smart, they created a fake reality. And we think we're moving in this fake reality, but no, we're not. We're nothing but people in a pod that's being used as a battery for the aliens. Well, that's the movie The Matrix. But some people think that, well, can you rule it out? Well, I think so. First of all, if you take a look at the weather report only goes for just a few days into the future. Why can't we simulate the weather 100 years into the future? Because the weather consists of billions upon billions and trillions of air molecules. Each air molecule obeys the laws of physics. And the laws of physics, even though you can model an air molecule, there's so many of them. There's so many air molecules that it would exhaust the power of an ordinary computer to model the weather. In other words, the smallest object that can model the weather realistically, that can predict the weather 100 years into the future, is the weather itself. So when we say that the smallest object that can model something is the model itself, it means basically you can't do it. You cannot simulate it. It's simply too complicated. And that's the weather. That's why the weathermen and the weatherwomen only go just a few days into the future. After that, all your computer projections are nonsense. And once you go to the quantum theory, it gets even worse. So in other words, I don't think we live in a simulation. Science Fantastic with Professor Michio Kaku. On Science Fantastic, we now have open mic on Science Fantastic, meaning that you can get on national radio and ask that question, make that comment that's always been bothering you. Some people say that they're walking down the street, just minding their own business, and they see the mountains, they see the clouds, they see rivers, and then they wonder, where did it come from? How old are they? Why do we have the shape of the mountains as they are? What shapes the clouds? And then you see the night sky, and you see the moon. You see the stars, and then you begin to wonder, where did it all come from? What does it all mean? And some people feel like they're nothing but a leaf blown in the wind, that they have no control over their destiny because they don't know where they fit into the larger scheme of things. Well, find out. I'm a scientist. I can tell you why the mountains are shaped the way they are, how the clouds form, why the stars twinkle. This is all a matter of science. Well, what I'd like to do now is answer some of the email questions that I get. And because, well, to be frank, some people are a little bit shy about asking your question on national radio. So some people prefer to simply email me. So let me answer some of the questions that I get. One set of questions I get is about the Space Force. Back in 1947, that was the last time that a president of the United States, President Truman, authorized the creation of a new branch of the armed forces. Back then, it was the Air Force. And there was a certain amount of bureaucratic resistance to it because the Navy had planes, the Army had planes, and here was a new branch. It was sort of like taking an arm or a leg out of the Navy and an Army and creating a new branch called the Air Force. Well, now President Donald Trump wants to create a Space Force, and again we have a certain amount of resistance from the Air Force this time, because it's like pulling an arm, pulling a leg out of the Air Force to create the Space Force. But let's take a look at the science now, not the bureaucracy, but the science behind the Space Force and what's really happening. First of all, we can't be naive, and that is the Russians and the Chinese, yes, they're also experimenting with space weapons. In fact, the Chinese, about 10 years ago, even blew one of their satellites right out of the sky, creating a tremendous amount of debris and pollution in outer space. And of course, the Russians can do it. We can do it too. In fact, the Russians even announced that they're experimenting with laser weapons that could conceivably knock out a satellite with laser beams. So let's not be naive about it. Other people are working on it too. So why not be the cop on the block? That's the pro side. The pro argument is, why not give a certain amount of order to the whole space race? We're going to have more and more spacefaring civilizations in space, so why not be the cop on the block? However, there's the reality of what a war may look like in outer space. First of all, the Russians have said that if we go for a space force, they too will begin a militarization of their force. And what would a war in outer space look like? Well, it wouldn't be very pretty. First of all, even a small nation, a nation like North Korea, could, in principle, detonate an atomic bomb over Kansas, creating an electromagnetic pulse, a shock wave, which would knock out half our satellites, blinding us, and knocking out most of our power plants on the planet Earth. Now, that would set us back 100 years. Think about it. The military would be paralyzed. We wouldn't have any eyes or ears in outer space anymore. Power plants would go down, creating blackouts over all of North America. Within a few days, we would have food riots because all the refrigerators would go on the blink, and there's no one to fix it because they, too, in the nearest city, they, too, had their power knocked out. So, in other words, a war in outer space is not going to be a pretty thing. And any country that wants to fight a war in outer space has to be prepared for a worst-case scenario, which is the electromagnetic pulse set off from an atomic bomb in outer space. Now, we know this. This is not science fiction. We know this because we've actually detonated atomic bombs in space, and it created a tremendous amount of havoc. Welcome back to Science Fantastic with Professor Michio Kaku. The lines are open. Now we're reading some email questions that I get because, well, to be frank, some people are a little bit bashful about having their voice heard on national radio. Well, another question I get is about the heat wave. Look, it's summertime now, the dog days of summer, and many people head on to the beach. But some people are noticing, well, this summer seems to be hotter than normal. And in the Middle East, the desert has never been as hot. World records are being set, and some climatologists are saying that if you peek into the future, of course, decades into the future, certain areas of the Middle East may be unlivable. And some people say, aha, it's global warming. Other people say, not so fast, not so fast. Well, first of all, I'm a scientist, and we realize that you cannot say with 100% certainty about anything, because you have to test it. You have to run experiment after experiment. And with 90% confidence, not 100%, but with 90% confidence, a majority of the world's scientists believe that the Earth is heating up and humans have something to do with it. Now, even the skeptics of global warming admit that the Earth is heating up. We know that for sure. We can measure the temperature of the Earth from outer space. We can see that the glaciers are receding, that cracks are forming in the South Pole, and the average temperature is rising as sea levels rise. So this is something that we all agree upon. The disagreement comes from the question of human intervention. How much of it is a natural cycle? How much of it is human? And when you look at human behavior versus natural cycles, you realize that most natural cycles take thousands of years. Thousands of years. The last ice age ended 10,000 years ago, and we may have another ice age 10,000 years from now. But it turns out that we're in the middle of an interglacial period, but the temperatures just within the last 100 years have been rising dramatically, especially the carbon dioxide level. And that's why you can say, not with 100% confidence, but with 90% confidence, that humans may have something to do with the fact that the Earth is heating up. Now, does that mean that the heat wave that is hitting the Middle East, the heat wave hitting California, creating forest fires, is that caused by global warming? Well, again, global warming is an average effect. There is no one-to-one relationship. And anyone who claims that, this is the fingerprint of global warming doesn't know what they're talking about. Global warming is an average effect. Over a period of time, you can see that on average, temperatures will rise. On average, sea levels will rise. On average, glaciers will begin to recede. But you cannot say that any one particular hurricane, you cannot say that one particular storm is due to global warming. But like I said, with 90% confidence, most climatologists with the computer programs can say that on average, the Earth is heating up, and we see that everywhere we look on the planet Earth. Well, we have another story, and this is about Alzheimer's disease. Alzheimer's disease, some people think, could be the story of the century. Baby boomers are getting older. And by the time you're in your 80s, a good fraction of the population naturally comes down with Alzheimer's disease, even if you've been healthy all your life, even if you have no genetic markers, and even if you seem to be totally fit. You too can come down with Alzheimer's, because a certain fraction, bordering on about half, of people in their 80s to late 80s naturally come down with Alzheimer's. So why don't we cure it? Well, first of all, we don't know what causes it, but a breakthrough was made just last week in order to understand the origin of Alzheimer's. First of all, if you do a test on Alzheimer's patients, you find a gum that gums up the brain, but scientists didn't know whether it was a cause or an effect of Alzheimer's disease. Well, beta amyloid protein is the gum that gums up the brain of people with Alzheimer's disease, but sometimes people have gum in their brain, but they're still very clear in their thinking. So it's not a one-to-one phenomenon. Now we know that the tau protein originates first and then creates the beta protein. But then the question is, where does the tau protein come from? And that was a minor breakthrough made just a few weeks ago. The scientists were able to show the molecular origin of the tau protein, which goes berserk, creating the beta amyloid, which then gums up the human brain. Now, does that mean that we can reverse Alzheimer's? No, but it means that in animals, scientists have been able to isolate that point where the tau protein goes haywire, and they've been able to slow down the progression of Alzheimer's in animals. Now they're trying it on humans. So it does not mean a cure anytime soon, but it does mean that we're onto something. For the first time, we have a solid lead that, yes, we can now see the biochemical mechanism by which the tau protein goes haywire, stimulates the beta proteins to create the amyloids, which then gum up the human brain, giving you what is called Alzheimer's disease. That is not a cure, but we're onto something. Well, unfortunately, our time is up on Science Fantastic. Good day.